Good morning, everybody. Welcome to episode 6 of AlgorithmsThread. I'm your host, David Harmeyer, and today we'll be talking about convex hulls and some cool things you can do with them. So before we start, I gotta mention this rebranding that's happening. So initially this was called AlgorithmsThread. It was a pun off of Algorithms Live. But this great guy, Frodikin, I don't really know how to pronounce his name, maybe Frodixian, he sent me a message and he was like, you know, you could, instead of calling it Algorithms Dead, you could call it AlgorithmsThread. It would match up perfectly with your handle, which is second thread, and everything would be amazing. And also, you no longer have the negative connotation of death. So I'm like, well, how can I say no to that? It's a fantastic idea. We've got to do it. So now this is officially, the series is officially called AlgorithmsThread. Maybe like the Algorithms Thread. Kind of makes sense. The thread where you learn algorithms. So yeah, hope you enjoy it. If, like, for some reason everyone thinks this is a stupid name, we might go back, but I think this is pretty cool. It's definitely a pretty huge improvement in my opinion. So there we go. All right. So today I'm going to be talking about convex hulls, and then also, because I don't want to bore people who know convex hulls already and know how to take the convex hull of a set of points, stuff like that, I'm going to go over some slightly harder stuff. So I'm going to do a bunch of pretty high-level algorithms that you can use convex hulls for. And then I'm also going to talk about some problem that is, like, it involves convex hulls, but it's not super obvious why. And I thought it was quite a cool problem when I saw it in contest for the first time. So I'm going to go over that problem too. You might want to hear that problem description and then pause it for a while to think and then see if what you thought of matched the solution that I used. All right, so the first thing to keep in mind, or the first thing to talk about, I guess, is let's say you have some polygon. The convex hull problem is basically, let's say, well, I mean, if you might have a polygon, maybe you just have a bunch of points. You can imagine these are all like nails in a wall, right? So you've got some wall, you nail a bunch of nails in. And now the question is, if you took a really big rubber band and you stretched it out, and you like put it out like this, and now you let the rubber band shrink to all of the points, what does it look like? And in this case, what would happen is the rubber band would like go around the nails kind of like this. That would be how the rubber band would shrink, and like it can't get any smaller. So that's like one way of describing it. If you had like some rubber band, how would it collapse around the points? You can also think about it as like all of the points in this area represent all of the points where if you're at some point here and you walk in any direction, you get closer to at least one of the points in this set. So here, if we walk in this direction, we're getting closer to this point. If we walk in this direction, we get closer to this point, and you can try it for all of the different directions in this circle. In every direction, you'll get closer to some other point. So the question is, if we're given a bunch of points, how do we find what this convex hull is? And there are a couple ways of doing it. I'm not going to go over all of the different algorithms because they're a bunch, and it's not really important to know all of them, just kind of how to do it in general. But I'm going to go over the algorithm that I use, and the algorithm I think is probably easiest and most helpful to implement. So you've got a bunch of points. What we're going to do is we're going to try and find the convex hull in two parts. We're going to find the lower hull here, and then we're going to find the upper hull like this. If we find both of those, it's pretty easy to combine them. We just first have the lower hull, and then we have the upper hull backwards. And that's the convex hull, and we go in counterclockwise order because that's the same order that the unit circle goes in. If you wanted, you could do clockwise order and everything would just be backwards for you, but that's fine. Okay, so this is your convex hull. How do we actually find this? One thing to keep in mind is every time we have two adjacent edges, we're always going to make, like if we're going this way along the edge, we're going to turn left. So this here, if we kept going straight, a straight line would look like this. So we've turned left here. And then similarly, we've also turned left here, we've also turned left here, and then like we keep turning left all of these times. If you have some other polygon that isn't convex, that means there's going to be some point, if you go in counterclockwise order, that you'll turn right. There will be some angle that's bigger than 180 degrees. So what we want to do is we can process all of these points in such a way where if we ever turn right, we want to erase the point that caused us to turn right. So maybe we have like this pattern here. So we check this edge, then we check this edge, then this edge. This right here is a right turn. And since it's a right turn, what we can do is we can get rid of this point, and instead we can go straight to this point. That way we won't have any right turns here. So to actually implement this, it's pretty straightforward. What you need is you're going to need one method to check if it's a right turn or a left turn. And you can do that with cross products, so I won't go through all the math. But basically, if you have two vectors, so this is like v1, and then this is v2. If you want to see if v2 is to the left or to the right of v1, so like if you imagine you take these two vectors and you line them up so they start at the same point. Now you want to see if v2 is to the left or to the right. What you can do is you can do the cross product. So the right-hand rule, v1 cross v2. This will be positive if v2 is to the left. Because like if you put your fingers at v1, curl them towards v2, your thumb comes out, which is like positive. And if it's on the other side, like you can imagine that would be very similar. If it were over here, maybe this is v3. So now v1 cross v3. That'll be negative because your fingers would or your thumb would have to go into the page. So that can have you pretty easily check whether you turn left or you turn right, or you go straight. Straight, obviously, if the cross product is 0. All right, cool. So that's all very basic. So now we know whether we make a left turn or a right turn. What we can do to get the convex hull is we're going to do this twice pretty much. We're going to do it once for the lower hull and once for the upper hull. And I'll just go over the lower hull. The upper hull is pretty much the same. So if you sort your points in increasing x order, and then if you tie break by y basically, then what you can do is we can process the points one by one. So first we'll start with this point here. We'll include that in our convex hull, so that's fine. Next we'll look at this point. So we can just include this in our convex hull right away. And the next point in the list will be this point here, so we can include that one as well. But the issue here is now we've just made a right turn. So when we make this right turn, we need to get rid of this top point and replace it with just an empty space. So now we have, instead of that point, we have this edge right here. So we've gotten rid of this point. Okay, the next x is probably this one here. So we will make that edge here. The next edge is this one, so we'll make this edge here. Again, we've just made a right turn, so we have to get rid of this point. Now we'll have this in our convex hull. Oh, I guess I was kind of mistaken. This one would be next, but if we let's move this over here. Okay, so now we have this bottom point next. So we'll see again, this is a right turn. In this case, we'll get rid of this point, and we'll have this edge here. Now, there's one case that won't show up in this polygon, but it's possible, and that's something like this. So maybe next we visit this, and then we visit this, and then we visit this. Next we have this point here. So here, this turn right here is a very sharp right turn. So we can get rid of this point, and that's safe to do. And when we're done with that, we'll have something that looks like this. Now we still have another right turn here. So we have to make sure we get rid of this point here. And basically, in implementation details, the equivalent here is we have to use a while loop instead of just an if statement. But that's fine. So yeah, so we keep doing that. We have this, let's say that's a left turn, and then we have this. Now we have our lower convex hull. We can process each point in order 1. We just add it to the stack of points that we have, and we see the last 3 points on the stack form a thing going in the correct direction. So do they make a left turn if you're doing the lower hull, or do they make a right turn if you're doing the upper hull? And if they don't, then you have to pop the middle thing and remove the middle one from the stack. Okay, so that's how you find the lower convex hull. You can find the upper convex hull the same way. I guess with these simplified points, it would be rather simple. And then once you're done, you have just these points. These are your convex hull. You've got the lower and the upper one, and then you can, if you want just like one convex hull for whatever reason, you can combine them by making these edges all go backwards. So now we have our convex hull. Usually people just store a convex hull as like an array of points or a vector of points. Okay, cool. So that is how you make your convex hull. The next thing I'd like to talk about is like just kind of a short side topic because we're going to use it a bunch, and that idea is ternary search. So you've probably heard of binary search. When you binary search something, maybe you've got some function here, and it's like an increasing function, and you want to see when it hits a certain value. So you can check an x here, you can check an x here, or well, you can check an x, and then you're like, okay, this x is too small, and you know the function's increasing, which means the range you need to check will change to this range. And every time you check a value, you cut your range in half, which means like the next time you check a value, maybe you check this x here, and now you can cut your range into this part. And then the next x you check might be this one, now you cut your range into this part here. So every time you check a value, you cut your range in half. And you can approach like some value very quickly in log time. So with a logarithmic number of checks, you can find the answer to whatever you're looking for. So that's binary searching, and that's pretty straightforward and pretty well known. Another thing you can do, which is very similar to binary searching, is called ternary searching. And I'm just going to go over that quickly because we'll use it quite a bit. So if instead of your function looking like this, instead of it being strictly increasing, if you know first it decreases, then it hits some optimal value, and then it increases, or like alternatively if it looks like this. It's okay if you have multiple best values here, but if it looks something like this, then what you can do is you can find this minimum point with a similar method. So now binary searching means you split it into 2 halves. Ternary searching means you just split it into 3 halves. So you're going to check maybe 2 points like this. And what you want to see is you want to see which of these 2 points is better. So we're looking for the minimum. So in the minimum, we want it to be lower, basically. So we know that this half is higher than this half, right? Or we know the lowest thing in particular isn't going to be in this half. The reason we know that is because if it were, then we would have this point here, we'd have this point here, then we have to have some lower point. And if our function goes up and goes down, then it doesn't follow this U rule that we described earlier. So what we can do is, if we know this point is lower than this point, we can get rid of this entire part of the graph. So we can narrow our search space down. And if we do it like this, we can get rid of 1/3 of our search space each time. So in like 60 steps, we can get as accurate as we need to be. And this is also in logarithmic time. Another thing you can do that's just as good is instead of checking 2 points that are very far away from each other, you can check 2 points in the middle that are really close to each other. And that way you can cut off like a very big section. So this might be like half of the data. You have to be careful if these are doubles because they might get really close. So you don't want to, like these might evaluate to exactly the same double. That's the thing to avoid. So you don't want to make them too close. If you're binary searching doubles, usually I just do 1/3 and 2/3. But yeah, so that's if you're binary searching like integers, if you're ternary searching integers rather, then it's safe to do 2 adjacent integers because you know the answers will be discrete. You won't have double precision issues. Awesome. Okay, so that's ternary searching. So how is this useful in the context of convex hulls? So there are a bunch of things you can do with convex hulls. I have them written down because I don't want to forget any of them. But one thing that's like really helpful and comes up quite a bit is point in convex hull or convex polygon. So as the title of this problem would imply, initially you've got some convex polygon. Maybe it looks like this. Then what you have to do is you have to answer a bunch of queries, and each query is going to be of the form, given some point here, is this point inside, outside, or on the border of the convex polygon? And let's say, for the sake of argument, all the coordinates are really big. So all the coordinates go up to 10 to the 9. If you ever see that in a geometry problem, what that likely tells you is you probably don't want to use doubles. So you probably want to do all of your math using longs in Java or longs in C++. And like we mentioned with cross products, all you need is a vector cross product to see which side of a line something's on. So that's all you need for this problem as well. You don't need to use doubles anywhere. You can do all of this math just with longs, with vector cross products and vector dot products. So we'll have this convex hull. Now we want to see, is this point inside or outside the convex hull? To make this problem simpler, what we can do is we can split our convex hull up into 2 parts. So we'll have this lower hull here. We'll also have the upper hull here. We'll have the leftmost and rightmost point in both copies of the hull. That's fine. And then what we need to do is there are really 3 cases, right? It's either above the polygon, below the polygon, or inside the polygon, or it could be on the polygon. But if it's inside the polygon, all we need to be able to check is for one of these hulls, is it above or below this half of the hull? And it's going to be inside if it's below the top hull and above the bottom hull. It'll be on the polygon if it's on one of the two hulls, and if it's above the top hull or below the bottom hull, that means it's outside the polygon. So how do we evaluate it for this hull? And if we know how to evaluate it for this hull, we can very easily see which side of the polygon it's on. So what we can do is we can just binary search. Actually, we can binary search which point or which edge is relevant. So first, maybe we'll look at this edge, and we'll see, okay, the point is to the right of this edge. So this is like the x coordinates that this edge is responsible for. It's to the right of that edge, and that means that we need to make our search space be these edges here. So if our search space is these edges, we can look through all of these somehow very quickly, and then we can figure out which thing it's under or above. And eventually, in log time, since we're binary searching, we can find the edge that's relevant. And now it's very easy for us to check, okay, we know it's going to be in this range here. All we need to check is, let's look at this vector. Let's use a different color. So there are too many things going on here. So we know this this edge is important. All we need to check is for this vector here and this vector here, is this a right turn or a left turn? In this case, if you go from the edge to the other vector, that would be what, a right turn. Since that's a right turn, that means it's below this half of the polygon. If you do that for both the top and the bottom hull, you'll figure out whether the point's in the convex polygon. You can do that in log time. Okay, very cool. In a regular polygon, you can do that in linear time, and that's a cool algorithm as well, but that's, I guess, something for later. Yeah, so the next thing that is fun to talk about is, let's say we have some convex polygon. What we can do is we can find the farthest point in some direction. So what do I mean by that? Let's say this is our convex polygon. We want to find the farthest point going this way. And the first thing to notice is that's not going to be a point on the edge. The farthest point in some direction, it's always going to be one of the convex hull points, right? There's not really any reason for us to care about it being like halfway through an edge, because if you're on the edge, if the edge is perpendicular to this, well, you could just pick one of these points as well. That would be just as good. And if the edge is maybe like this, then if we're at this point here, we can just move over to this end point of the edge. Okay, so equivalently, we want to maximize the dot product with this vector. The dot product just indicates like how much do they go in the same direction. So if you treat all of the points on this polygon as vectors from the origin, maybe the origin's like right here, we want to see which point has a maximal dot product with this vector. And it's going to be this one here dotted with this. That'll be the biggest you can get. So we can do this in a very similar way. We'll have this upper polygon, and we'll also have the lower polygon, or lower hull. And this time we can ternary search. So what we'll do is we're going to check for both halves. We'll find the answer for both halves, take the better one. For the top one, let's check these 2 points here. So if we check these 2 points, and we see this one is better, then we can cut off this half of the range. And really, it is half of the range. It's like half of the range minus 1, maybe, because we're checking 2 points that are right next to each other, not necessarily like 2 points next to the same edge. So you can think about it as binary searching the edge or ternary searching the points. And then we can do the same thing for these points, and now we'll be left with these 2 points, and eventually we'll just be left with like either 2 points or just 1 point depending on how you implement it. And when I say 1 point, like it's actually safe to, when we see this point is better, it's actually safe to cut off this point as well. We cut off that whole side of the polygon since we know edges aren't important. Okay, so yeah, that should be pretty clear how you can do that in log time as well. This isn't point in convex polygon anymore. This is farthest point in some direction. But yeah, so there's that trick as well. So now one problem I'd like to go over. It's an old ICPC World Finals problem. All right, so you're given some piece of garbage. Looks like this maybe. And what you have to do is you have to find the smallest garbage can that you can put this piece of garbage in. The way you're going to put it in the garbage can is like you'll have some some slot here, and you can take this piece, you can rotate it however you'd like, and then after you rotate it, you just have to slide it straight through the slot. And that's, like, you can't rotate it as you slide it through. And what that means is basically what we're trying to do, I think this is called like the 2 calipers technique maybe, but what we're going to do is we're going to try and measure the smallest that this is ever going to get. So we can do this in a bad runtime pretty easily, because one thing we know is what's going to wind up bounding the width of this garbage can is going to be a couple things. But basically, let's imagine we have 2 parallel lines, right? And we're going to take these 2 parallel lines, and we want the distance between them to be as small as possible. But we can like rotate the angle of the parallel lines if we need to. So maybe you think this is the optimal answer. Well, we can show that this isn't going to be the optimal answer as I've drawn it. And the reason that's the case is because we've got this this line here, right? This is kind of the line between the 2 points we're drawing this line between. If we take this line and we rotate it a little bit like this, then the distance between them is going to be smaller. We've now created a smaller trash can that works. And we can do this as long as there are only 2 points touching the ends of the garbage can. So we could slowly rotate it, and we can imagine that that would be a valid move all the way up until these garbage can lines look something like this. So if it looks like this, we have this line, and we can't rotate this line anymore. But we also, like, we could rotate it more, but if we would rotate it more, then this line here becomes the new farthest line between any 2 points. So we have these 2 conditions, and we have to make sure both of them are satisfied. And like from that argument, we can see that the best answer is always going to be something where we can define it by 3 points. So 2 points will define some edge, that'll define like the direction, and then the farthest point away from that will define the length of the garbage can size. So we could really easily do this in n cubed now. So now we have this n cubed solution. This is just iterate through all 3 pairs of points. First, this pair here will define what this edge is, and then we want to find how far does the polygon go in either direction of that edge. Yeah, okay, so that's one solution. One thing to keep in mind, though, is that if you imagine you've got your polygon, if you were to take your polygon and like put a rubber band around it, take the convex hull of it, you'd get something that looks maybe like this, right? You'd extend these lines. It should be pretty clear that there's no reason this would make the polygon harder to fit in some trash can. Since we have to move the polygon straight, we can't like rotate it as we push it down through the trash can, then we can never use this space. We're gonna take some, like this will be the edge of the trash can, right? This is just gonna move in some straight line. If the edge of the trash can moves into this space, then we won't be able to push the item through the trash can at all. It'll hit the item. So we can take the convex hull and then we're safe. And that's like one optimization we can do. And if we do that, we know now the only edges that we have to check, the only things that will slide against the edge of the trash can, are going to be some edge on this convex polygon. So now, by doing that, we've reduced the number of edges we have to check from n cubed to just n squared. So we'll brute force this edge on the convex polygon. Now we have to find what point would be most constrictive, what point would be the strongest requirement that we have to pay the most attention to. And that will define how big the trash can will be. All right, we can do it even better. We can do it in n log n. And I think for the problem, bounds were so small, for the world finals problem, bounds were so small that I think even the n cubed was fine. So you didn't really have to make any observations at all. But I think this is an interesting problem, and bounds could have been bigger, so we should know how to solve it if they're bigger. Yeah, so if you have this n log n, what you can do is you can brute force this point on the convex polygon, or this edge on the convex polygon, And then what you want to do is, since you've taken a convex hull, you can find the furthest point in some direction. The direction we'll choose is the direction perpendicular to this edge. And we want to find the farthest point in that direction. We just learned how to do that. We can do that in log time. We can make some method that does it, not worry about it, and just find this farthest point very quickly. And clearly that farthest point is going to be the most constrictive restraint. So there we go. That's our n log n solution. You can also do it in order n. So there's also that. The order n requires having a convex polygon though, and you're going to have to sort your points by x's anyway. So your final runtime is really just going to be n log n. But you can do it in order n with like a 2-pointer sweep, where you rotate both the point and the edge at the same time. I don't think that's too important though. The important part is knowing how to use the farthest point in some direction. Awesome. So that is the garbage collection problem. The final problem that I'd like to talk about is called troop mobilization. So this was from, I believe, 2018 Southeast Regionals for ICPC. And like I competed in this contest live, so I saw this problem as a contestant. We did end up solving it. It was quite a cool problem. I really enjoyed it. But basically for this problem, the way it works is you have a bunch of different troop types. So you have n like types of troops. And each troop has a couple things. It has like some health per unit. It also has some like attack per unit. And it also has some cost per unit. So you have each of these different values, and so maybe you've got like one troop type is like, maybe it's like a tank, so it's got like a 10 health, has 2 attack, and it costs 10 to buy 1 tank. Maybe you have just a soldier, and your soldier is just like 1 health, 2 attack, and it costs 2 to buy the soldier. So what you want to do is you have like maybe you have X dollars to spend, and you can spend your dollars on troops however you would like. And you want to maximize the like some value, and that value is going to be the sum of the healths times the sum of the attacks of all troops you buy. So one other important constraint of the problem is that you can buy fractional troops. So you can buy like half of a soldier, or you can buy like a tenth of a soldier. You can buy any real number of troops. You don't have to buy like a full tank. You can buy half of a tank if you'd like. And one constraint there, I guess, is that you can do that as much as you'd like. And if you buy like half a tank, it costs half as much. You get half as much health and half as much attack. So yeah, the question is, now you have all of these abilities of things you can buy. How do you maximize this total power of whatever army you wind up with? All right, so if you'd like to think about that, now might be a good time to pause, maybe work out some stuff on paper. It's not too math heavy, you shouldn't need to do too much, but it's like a very interesting problem, so it might be worth trying yourself. All right, you've been warned. Time for spoilers. This is the solution. Okay, so what we can do is we have these different troop types, and we currently have like 3 different dimensions. We've got this attack, this health, and this cost, and we can think about these all as 3-dimensional points. Each troop type has some health, some attack, and some cost, so it's a point in 3-dimensional space. However, that's a little bit annoying to think about, and we can really easily get rid of this cost. The reason we don't care about cost at all is because we can buy a fraction of these troops. So maybe this is a tank and the tank costs 10, but we could look at 1/10 of a tank, we could make that our new unit, and if 1/10 of a tank is easier to think about, then we can solve like anything we could do with full tanks, we could also do with tenths of tanks. So now with the health here, instead of being 10, it'll just be 1, and the attack will be, I guess 1 or 2 tenths. This will be, yeah, we'll just divide everything by 10, right? So this will be 10 tenths, this will be 2 tenths. And then for this tank, it'll have 1/10 or 1/2 health, and 2 halves attack. So now what we have is we have these tanks here instead of, or these points here really, instead of these three-dimensional points. And the great part about this is now we have 2D points, and they're easy to think about, and also everything has the same cost. So we don't need to concern ourselves with cost at all. We just have like a total amount of cost that we can spend. To make it even easier, since we have maybe C dollars total, right? What we can do is we can divide all of these costs by C again. And if we do that, then it's as if we start with just a total amount of like $1. So now the question would be, like, for these, how much health and how much attack do you get if you spend all of your money on this troop? Awesome. So now we've removed a bunch of parts of the problem, and we just have this thing where, like, okay, we can take as much of this as we want, we can take as much of this as we want, and what we want to end up maximizing is the sum of our attacks times the sum of our healths. When I say we can take as much of it as we want, I mean, like, this can be as big a proportion of your total spendings as you'd like, but you can only spend a total of 1. Okay, so now I guess a good follow-up question would be, what can we buy? If you've got 2 points like this, what you can do is you can buy, if you buy like maybe half of this and half of this, what will that look like? Well, you have a vector that goes halfway here, and then a vector that goes halfway here. When you add them together, you'll get something like this. That's kind of a, let me draw more accurately, there you go. So this looks like it's the midpoint, and it should be pretty clear that it is, because you get half of the attack of this, you get half of the attack of this, and then you get half of the health as well. So you're halfway between the x's, halfway between the y's. That's going to be the midpoint of these two. And that was if you buy half and half. The same argument would apply if you buy a third of this and 2/3 of this. So it should be pretty clear we can get this point, we get this point, we get all these points on this line by just buying different proportions of this first one and then the opposite proportion of this other one. Opposite being like 1 minus that. So we can get all of the points on this line really well, and anything we have there is something that we can buy. We can get any combination of these points. All right, cool. So the next thing to keep in mind is this is if we just have 2 points, or if we have maybe a bunch of collinear points. If we have points that aren't collinear, I guess the title of this episode might kind of spoil where I'm going, but it's kind of interesting, I think. So let's say we have this third point here. We can get this point, and we can get any point on the line between these two, and also any point on the line between these two. But instead of getting one of these discrete points, what we could do is we could take some like combination of them and maybe get this point here. So we can also get any point on the line between these two, and any point on the line between this and anywhere on this line. So we can get all of this stuff as well. So really we can get any point that's within the convex hull of these 3 items. So that's why this is a convex hull problem. But we haven't solved it yet. So far we've just determined, where we've simplified it quite a bit, but we still want to determine what's the biggest answer we can achieve. So what does this answer look like? Well, if we pick some point, the value of that point is going to be its x times its y. You might be concerned with, like, what does that mean we're trying to optimize for? Well, it seems like, sure, you want to increase x's, you also want to increase y's, so you want to go farther roughly in this direction. But it's not just absolute value of distance from the origin, because maybe you can have a y of 10 and x of 1. That's not as good as having an x of 4 and a y of 4. This would be a better combination. So what you can do is, if you imagine plotting, like if we have some graph here, if we imagine plotting points that all have the same value, they're going to look like this. So I think this is the graph of y equals 1 over x. Right? And if we imagine what that means, like this is equivalent to y times x equals 1. And so that means the value of this curve is going to be equal to 1 everywhere along the curve. Well, if we want it equal to 2, we could have a similar thing, right? 2 would just be something like this. Be some curve like that. And then as we increase the value, we have another curve that's farther and farther out, right? Because they have better and better values. What we want to see is, what is the farthest curve that intersects this convex polygon? And that seems initially like it might be a tricky thing to do. But the great part is we've learned how to do ternary search. And it should be pretty clear that if you have some edge here, if we have an edge like this, the best point is going to be this endpoint. But we might also have some edge that looks like this. If we have this edge here, initially this is a pretty bad answer. As we move down the edge, the answer will get better, and at some point it'll be optimal. But then after that, it'll start getting worse. So the function for this edge will be exactly that U shape, or I guess the inverse U shape. It'll be like a frowny face, or an umbrella, I guess, that that we can ternary search. We can find the minimum point here. So we can do this for every edge. We'll just look at every edge in the polygon. The answer is going to be somewhere along one of those edges, because otherwise you could just move up and to the right, and you just make your answer better. So the answer is going to be on one of those edges, and you can ternary search on this edge where you want your optimal position to be. And like to do that, you just check 2 points and then cut off the third that's worse. So yeah, that's kind of a cool convex hull problem. It's not super obvious when you first look at it, but it's helpful. I think it's a good thing to know. It's also really creative that like some problems that don't at all look like geometry when you first see them turn out to be geometry problems that aren't too terrible as long as you have the book code or the hackpack code in order to do the easy stuff. All right, so hopefully you found that interesting if you already knew convex hulls, and hopefully if you didn't know convex hulls, you kind of now have a feel for it. I do recommend upsolving this if you're looking for some practice with ternary searches, and you should definitely write your own like convex hull code so that you have that for contests where this kind of stuff might show up. Yeah, so thank you for watching. Let me know what you think about the new name, if you like it, if you think it's a bad change, if you think it's as cool as I think it is. And that's all. Yeah, I'll see you in the next algorithms thread. Goodbye.